Let's jump right into the various time scales we see in the tropics. And this is easier seen with the variance in OLR, the outgoing long wave radiation, because it is a measure of the convective activity, as we said before. And it captures these time scales that are from 2 to 10 days, which is the weather time scale, commonly referred to as synoptic time scales. Then you get into 10 to 20 day time scales, which are referred to broadly together with the 20 to 60 day time scale as the sub-seasonal or intra-seasonal time scale. So they are less than 3 months, which is a season, and these are considered high frequency sub-seasonal time scale, and these are the low frequency sub-seasonal time scales. Just looking at the variance in terms of watts per meter squared, you can see during the June, July, and September, October, November season, the dynamics we talked about before in terms of the trade wind changes, sun moving north, ITCZ moving, and so on. We looked at mean rainfall, mean winds, and so on, but those are not steady winds, right? There is always gustiness in these winds. The rainfall is never just drizzling. It's got pouring rain and then dry periods. So there are various rich spectrum of time scales involved in these, and ocean is responding as well to the demand from the atmosphere or the wind forcing the latent heat losses, evaporation, and so on. Ocean in general, of course, has a high heat capacity, moves much slower than the atmosphere. Atmospheric winds are order 10 meter per second, whereas ocean currents tend to be order 1 centimeter per second. So obviously there are huge time differences, time scale differences. Nonetheless, ocean and atmosphere interact on all these time scales, and we have to understand why. And broadly speaking, we have to understand also why these kind of spatial scales emerge from the coupled system. Why is it that rainfall is happening in these narrow bands, whereas we will see later on that the evaporation is happening on much broader scales to supply the moisture to these rain bands. They are not completely understood, but we will just at least think about those anyways. So OLR corresponds very closely with the rainfall patterns we have seen before. So you clearly see the ITCZ, SPCZ, and you see high rainfall over Bay of Bengal and the ITCZ here, West Africa rainfall, etc. But now we are looking at weather time scale, synoptic time scale, the high frequency intra-seasonal time scale. So you can see there are differences in the variances over, let's say, Bay of Bengal. High here and high here compared to this time scale here. We will see later on that there are also differences in terms of how they propagate. These are basically energies being moved. It could be energy being moved from here over to land as monsoon depressions, or it could be energy being moved from the marine ITCZ to the Bay of Bengal in terms of what are called monsoon intra-seasonal oscillations or northward propagating systems. And during this season you get very strong eastward moving systems called Madden-Julian oscillations, which are being generated in the western Indian Ocean and propagating eastward, either getting stuck here, getting detoured, crossing over, strengthening again, and so on and so forth. But you again see the gyres with low rainfall, upwelling region with low rainfall, and of course Somali upwelling here, and so on. So there is also obviously very low frequency, 1 to 10 year time scale, which obviously is dominated by El Nino in the tropics. But we'll see that there are also zonal modes of variability in the Indian Ocean and in the Atlantic Ocean at interannual time scales. And there are lower frequencies because of connections between each of these oceans. So Indian Ocean interacts with the Pacific Ocean, Atlantic Ocean interacts with the Pacific Ocean, and Pacific Ocean, which is like a monster with this huge rainfall, because the heat source condensation heating can drive global circulation, tends to impact the Indian Atlantic Oceans as well, and there are tropical extratropical interactions going on as well. So you can see that seasonally speaking, JJA doesn't have as much variance in OLR at this time scale compared to the SON, and we will see that the DJF also has much higher variability at that time scale because, again, El Nino happens at at this time scale with the El Nino peaking in DJF. Okay, so just remember those. You can see the difference here in the monsoon season creating the rainfall maximum here because of the Western Ghats, here because of the warm waters and the Burmese mountains, and here the marine ITCZ. But in SON it begins to look very different because the entire ITCZ that has moved north begins to recede, and you can see the SPCZ begins to pick up and so on here, right? And you can also see that in DJF and MAM. So look at this now. The DJF ITCZ is to the south, so the entire intraseasonal variability is higher here, and unlike the northward propagating systems here, we have eastward propagating systems here, and the detour of these can create the Australian monsoon and the impact on the South Pacific convergence zone as well. I have a talk on the MJO detours and impacts on SPCZ on YouTube that you can look up if you are interested. So the point to remember is that there are strong variabilities at synoptic time scale 2 to 10 days, intraseasonal time scale split between 10 to 20 days and 20 to 60 days, and low frequency variabilities at 1 to 10 years. Of course, there are lower frequencies. Monsoon has a multi-decadal variability of potentially at 20 to 40 years and so on. But extracting those from data becomes a problem because you have to have data that's long enough to get multiple cycles, and we end up relying on paleo data like from corals, tree rings, sediments, speleothems, etc. Okay, so remember the rich spectrum of time scales. There are also waves in the system that I'll come back and talk in the next podcast. I want to leave these intraseasonal to intraannual time scales by themselves so that you can absorb them. Don't panic if you don't understand each of the detail, because we're going to go into the details of all those phenomena in the rest of the course. There are 18 chapters where these things are described in various details. But as I said, look at these, you learn everything, and when you come back, it should all sound very familiar, even if this is your first time. Okay, that's the goal.